All right, let's dive right in. Today we're talking about the very language the universe is written in, physical quantities. These are the tools we use to describe and measure absolutely everything, from a tiny particle to a whole galaxy. So, let's get into it.
Just think about your day so far. You check the time, maybe you see a speed limit sign, you feel the temperature outside, you are constantly interacting with physical quantities. So, the big question is, how do we take this, messy, chaotic world and actually translate it into numbers we can work with?
Well, that's where this idea of a physical quantity comes in. And it's a beautifully simple but really powerful concept. It's not just a number, it's a number that has a unit attached to it, something that gives it meaning. Saying the number 7 means nothing, but saying 7 meters, well, now we know we're talking about a length. That's the key. Every single physical quantity needs both parts to work. A magnitude, that's the number, and a unit, that's the what.
So, here's the game plan for today. We're going to start with the absolute building blocks. Then, we'll add a new layer, direction. After that, we'll see it all in action with some real problems. And we'll wrap up with a little exam practice to make sure it all sticks. First up, the fundamentals. I want you to think of all of physics like a giant box of Legos. You've got these few, super basic, fundamental bricks. We call those base quantities, and you use them to construct literally everything else.
So what's the difference? Well, base quantities are the originals. They're the 7 core ideas that you just can't break down any further. They just are. Everything else, and I mean pretty much everything, is a derived quantity. These are what you get when you start combining those base quantities by multiplying them or dividing them. They're like remixes of the originals.
And it's kind of wild to think that so much of our understanding of the universe is built on just 7 base quantities. These 5 right here are the real heavy hitters you'll see all the time. Length in meters, mass in kilograms, time in seconds, electric current in amperes, and temperature in Kelvin. These are the official SI units, the global standard. If you get these, you have the foundation for almost all of physics.
Let's make this real with something we all get, velocity or speed. It feels pretty fundamental, doesn't it? But, surprise, it's not. It's actually a derived quantity. Why? Because you calculate it by taking distance, which is just a form of the base quantity length, and dividing it by another base quantity time. See how that works? We just built a brand new concept using our basic Lego bricks.
Okay, so we've got our building blocks. But sometimes, just knowing how much of something isn't the whole story. Sometimes, you also need to know which way. And this brings us to another crucial idea, the difference between scalars and vectors.
This is a really important distinction. A scalar quantity just tells you the magnitude, the how much. If you say a car traveled a distance of 100 meters, that's a scalar. It's just a number. But a vector gives you the whole story. It has both magnitude and direction. Saying a car's velocity is 30 meters per second north, that's a vector. The direction is a critical piece of the information. Think of it this way. Speed is a scalar, but velocity is a vector.
All right, enough theory. It's great to know the rules, but let's see how this stuff actually works in the real world. It's time to put these ideas into action and solve a few common problems.
Here's a classic one. You're given a speed in meters per second, which is the standard for science, but your brain and your car's speedometer thinks in kilometers per hour. So how do you switch between them? This is a super practical skill you need when you're working with physical quantities.
Well, there's a simple little magic number for this conversion. 1 meter per second is the same as 3.6 kilometers per hour. So all you have to do is take your number in meters per second, in this case 25, and just multiply it by 3.6. And boom, there you have it. 25 meters per second is exactly 90 kilometers per hour.
And just to really hammer home this whole derived quantity thing, check out this list. Force, pressure, energy, power. These are the titans of physics. And every single one of them is a derived quantity built from those basic units we started with. Each one even gets its own special SI unit, often named after a pioneering scientist, like the Newton, the Pascal, the Joule, and the Watt.
Now for another great example, and this is one that trips people up all the time, the difference between mass and weight. So let's say we have a stone with a mass of 4.0 kilograms. Now mass is a base quantity. It's the amount of stuff in that stone. But what is its weight here on Earth?
Here's the deal. Weight is a force. It's the force of gravity pulling on an object's mass. The formula is really simple. Weight is just mass times the gravitational field strength, which we're told is 9.8 newtons per kilogram here on Earth. So we multiply our 4.0 kilograms
by 9.8 newtons per kilogram, and we get 39.2 newtons. And notice the unit. It's newtons, the unit of force, not kilograms. That's the whole point.
Okay, let's try a more conceptual one. We talk about density all the time, but is it a base quantity or a derived one? More importantly, how would you prove it? Think back to our Lego analogy. Can you break density down into simpler bricks?
Let's trace it back. The formula for density is mass divided by volume. Okay, what's mass? Well, we know that's one of our core base quantities. What about volume? Volume is just length times width times height, right? It's built from the base quantity of length. So, since density is a combination of other quantities, in this case mass and length, it must be a derived quantity. It all comes back to the basics.
Now, before we get to our final practice round, there's one more quick but really crucial real-world idea we need to cover: uncertainty. See, in science, no measurement is ever 100% perfect. There's always a little bit of wiggle room based on how good our tools are, and we show this using the plus or minus symbol. So if we write 1.35 plus or minus 0.01 meters, it just means we're confident the true value is somewhere between 1.34 and 1.36 meters. All right, you've seen the concepts, you've seen them in action. Now it's time to put it all together and test what you've learned with a couple of quick exam-style questions. You ready for this? First challenge. Let's talk about work. In physics, work has a very specific meaning. It's all about what happens when you apply a force over a certain distance. So if you have a force of 10 newtons that pushes an object for 5 meters, how much work was done?
The formula for work is as straightforward as it gets. It's just force multiplied by distance. So we take our 10 newtons, multiply it by 5 meters, and we get 50. The unit for work and for energy is the joule. So the answer is 50 joules. It's a simple calculation, but it's the foundation for understanding energy itself.
Okay, second and final challenge. Let's bring back that idea of uncertainty. Let's say you measure an object's mass to be 2.0 kilograms, but you know your measurement has an uncertainty of plus or minus 0.1 kilograms. What is that uncertainty as a percentage?
To figure this out, you just divide the uncertainty by the actual measured value and then multiply by 100 to turn it into a percentage. So we take 0.1, we divide it by 2.0, which gets us 0.05. Multiply that by 100, and our answer is 5%. It's a really useful way to see how big an error is compared to the measurement you took.
And that pretty much brings us to the end. When you step back and think about it, we've basically just learned the alphabet of the universe. So the question I want to leave you with is this. Now that you have these fundamental building blocks, what incredible, complex things about our world can you start to describe just by putting them together? Thanks so much for watching.